Okay then, so let's start. And hi everybody, and welcome to our webinar, The Harmonization of Microplastics Analysis, with our special guest from the Alfred-Wegener-Institute, Sebastian Primpke. My name is Simon, and I'm going to be your host for this session. Before we start with the webinar, let me give you some tips and tricks that might help you avoid technical issues. First of all, please use the computer audio and not a phone call. This prevents video and audio from running out of sync and usually provides a higher quality audio. Please also check if the audio setup of GoToWebinar displays the correct audio device. But if at any point during the webinar or speaker change, you should face technical difficulties like audio cutting out or having no sound at all, don't panic. The issue is mostly the Windows audio settings. And if you have two devices connected, for example, a Bluetooth headset and laptop speakers, this can cause issues. Please try setting the preferred audio device as default device and default communication device. Afterwards, it should look something like this. And if this still doesn't help, rest assured that we will send you a recording of the event, including the question and answer session, to watch it later. Lastly, if you have any questions at any point during the webinar, please use the questions tab on the right of the interface. During the webinar, we will be collecting the questions to ask in the live Q&A session. And this way we will ensure a fluid and easy to follow discussion. But that's it. And without further ado, let me give the word to Sebastian Primpke, who's going to tell us about the harmonization of microplastics analysis.
Welcome to today's webinar on FDR and microplastic research towards a harmonized analysis. What are microplastics? Microplastics are defined as particles in a size range from 5 mm down to 1 micron. And within this size range, they can either be produced, called primary microplastics, or formed by breakdown of larger items, called secondary microplastics. These particles are currently further defined, for example, by the state of California as solid materials made of more than 1 weight% of polymers. And in terms of environmental research, why it's important to analyze microplastics. On the one hand, monitoring, for example by GISA, within the guidelines for monitoring and assessment of plastic litter in the oceans, requests the analysis of small-sized microplastics. On the other hand, all these materials may contain different chemicals like plasticizers or additives dependent on the polymer type. And risk assessment then needs all of this information on the particles, like their numbers, their shape, and also polymer type, to address potential impacts on human health, for example, human health. On the other hand, other users of this data, for example, wastewater treatment plants, need the polymer mass to address these plastics by mass balances. So we have now several types of analysis available to give us different types of information. For example, particle numbers we either gain by FDR spectroscopy or Raman spectroscopy. Both are using reference databases or other chemometrics approaches for identification, but differ, for example, in the diffraction limit. FDR can aim for larger particles larger than micron, which can also be measured in a rapid fashion, while Raman spectroscopy aims for even smaller sized particles down to 1 micron, but in contrast, the analysis time is rather high. If we aim for polymer mass, currently thermoanalytical methods optimal for use because they use degradation products for the identification. But on the other hand, in contrast to FDR and Raman, the sample is lost afterwards. Within the scope of this webinar, we will focus on air radiation interacts with a molecule by absorption at the different vibrational stages. For example, wedging vibrations in plane bending vibrations or out of the plane bending vibrations. And these different types and different elements present in the polymer then yield a fingerprint of the material. This fingerprint, or more precisely called fingerprint spectra, can be analyzed by, for example, library searches. So one example is shown here. We have this unknown material. We have spectral database containing various types of fingerprint spectra, and by chemometric approaches we then analyze it, for example, like here, as polyethylene. So how is such a spectrum collected? Here an exemplary spectrometer is shown, starting with a source compartment where global produces the IR beam, which is led through an aperture wheel and a filter wheel into the interferometer, consisting of a beam splitting mirror and two other mirrors where the light treated is fixed, and a moving mirror to produce an interferogram. This interferogram, or this is led through the sample and collected on the detector. By Fourier transformation, this information is transferred into a spectrum and can be analyzed with on. Why is FTR now optimal for MP analysis? On the one hand, we have different techniques available, which we can use, for example, for larger microplastics, larger 500 micron, and smaller ones. Secondly, we can apply chemical imaging. As AR microscopy is non-destructive, for example, we can analyze this whole complex sample here again and again and again. And compared to Raman microscopy, such a sample is analyzable with FTR, which is very limited using Raman microscopy. And finally, compared to Raman measurements, we have a fixed time frame for chemical imaging. So we can schedule and plan ahead how many analyses we can perform per day. Starting with the analysis of microplastics with particles larger 500 micron, these are typically sorted by hand by first a filtration step using filter meshes, for example with pore size of 500 micron, and afterwards optically sorted under a microscope in natural materials and suspected microplastics. All suspected microplastics afterwards analyzed using attenuated total refraction, ATR, FTR, and under such an instrument, an example is shown here, the particle is placed onto the crystal, in this case a diamond crystal. So shown here, this is a very fine particle, and then pressed onto it and measured. Here's an example of this larger sized particle measured with RTR, FTR. You see here a typical spectrum, so the particle in red, the assigned reference from the database in blue. In this case, the particle was analyzed with a hit quality 954 from 1000, so relatively high. For smaller sized particles, now two different pathways are available. On the one hand, we have the particle selection on windows and filters, and on the other hand, by chemical imaging, which is then followed by a manual or an automated analysis. Starting with the particle selection method, I show you one example. Typically, as mentioned, we place the sample on a filter or window and then select each of these particles. This can either be performed by the operator using identification guidelines, or by the instrument itself using, for example, dark light illumination or image analysis. Afterwards, a small field or point is assigned to this area, measurement performed, and followed by data analysis. I'll show you now one example on the sediment sample you've seen before, where we selected on a small field every potential particle and marked it with one of these small crosses. See here, for example, a round shaped particle with a cross here in the middle is then applied with an aperture of the instrument to reduce the air beam to a focus of 20 micron. This air beam is then led to a single element MCT detector for data collection. If we would not use an aperture, the whole field of view would be measured within this measurement, so not the selected particle. We performed this analysis on this area where we selected 104 particles and only 2 of these were identified as plastics. One example is shown here. Within simple, you see here the orange spectra, the measured spectra, and in blue the reference spectra. In this case, the sample was identified as polysulfone, which is rather used often in filtration setups, which was also the origin of these particles for this particular sample. On the other hand, if we go for chemical imaging, we can measure independent from the particle density on the filter. We can also measure large areas, for example here 10 to 13 millimeters in diameter, typically measured as a rectangular field, either in transmission or reflection mode. Again, this is the sediment sample shown before, and even if we have the problem of sample overload, for example like here on these corners by this so-called coffee stained filtration, we still be able to measure with this technique. For our samples, we already have a method to remove these filtration issues by applying a smaller diameter for the vacuum than the filtration area. If we now move such a filter into the air beam, we gain here an example for transmission measurement. As different lenses are available, one of the typical examples is a Cassegrain lens. See here the air beam moved to mirrors through the sample and it's refocused with mirrors to the detector. And by the application of focal plane array detectors, we are able to measure the whole surface of the, in this example, anodisk filter. An FPA is similar to a CCD camera, in this case made of MCT elements. Each element represents a pixel, and behind every of these pixels, a spectra can be found. Now, to analyze these individual spectra, several pathways are available. By, first of all, the manual analysis, one normally uses type of signatures. These signatures are typically produced by integration and were determined from different polymers to say, okay, have this spectrum here and look where can you do integration to cover most of the materials present. And 2 examples are shown here at 1430 wave numbers to 1480 and 700 to 1800. If we apply this now, we see a so-called chemical image indicating potential polymers. By zooming in, we can select these particles and then do a manual library search to identify the polymer, like in this example, polypropylene. This approach was already used in different studies. One example, using treated wastewater, was conducted together with the OOVV in Lower Saxony. Here we analyzed several wastewater treatment plants, including one having this post-filtration unit. We sampled at the effluent of the plants using 10 micron stainless steel cartridges and sampling volumes from 0.39 to 1 cubic meter. All samples were purified by enzymatic digestion, and we found in every sample microplastics with mainly polyethylene, polypropylene, polyvinyl alcohol, polyamides at some points, and in one example, quite a lot of paint particles. Also, we found quite a range in numbers ranging from a few particles after the post-filtration unit in Oldenburg to other large numbers, for example in Holdorf, meaning there are quite some differences between the wastewater treatment plants, but also in their yearly effluent. For example, the Holdorf, we have a high emission rate, while Neuharlinger's here, it's a rather low emission rate. But not only treated wastewater is affected by microplastics. If we look in drinking water, here the whole process starting from the source, the well, during the water treatment, due to the end consumer, we found that we can find very low concentrations of microplastics, but mainly either at the wells, for example in Holdorf, or in between, but not at the tap of the consumer. Still, when we did this analysis, we moved into an issue, because when we move into more complex samples like melted sea ice, we get this result from a first call image. So is it an easy task to analyze this? Let's have a closer look. There are a lot of highlights. And if we mark every potential highlight, you see that there's a lot of points. And in each of these points, you need to perform always this procedure. So select the point, do a manual library search, and identify it either it is a microplastic or not, and then proceed to the next one until you are finished. This is extremely demanding for the persons performing the process, and they most likely to develop a bias, but also they need a lot of time. So we need a lot of personnel to do this. And in conclusion, the whole process of manual analysis has a high expenditure of time due to the manual selection of the particles, manual library search, the size determination of the particles is limited in addition, and the whole process is prone to human bias. And included in this bias is also high demand of personnel, so high costs. And in total, when checking if you go for the standardization or harmonization of this process, one can conclude that this process is unsuitable for the harmonization of microplastics analysis. To achieve harmonization, we need to fulfill several requirements. We need a low expenditure of time for the whole process. We need an impartial analysis. It should have a minimum of personnel requirements, and the measurements need to be fast and reliable. And in our case, we aimed for harmonization by combining this FT imaging with the automatization of its analysis for microplastics. How did we achieve this? So our process is called automated analysis, and here we programmed Opus to perform two library searches for us. In this case, we were using correlations, first on the untreated spectra with spectrum normalization, and secondly on the first derivative of the spectrum with vector normalization. And it was then combined, shown here, as a two-step process. And both of these two steps need to yield the same polymer type to be successfully identified. With this method, we achieved an error rate of around 3% after manual analysis of all assigned spectra, and additionally can transfer this data into images. And here we implemented image analysis to quantify and also determine the sizes of the microplastics. And this is then a rather rapid process, and you've just seen how rather fragmented particles are brought into context of larger particles, fulfilling specialized requirements you can find in detail in the study below. With this image analysis, we're not only limited to, or we're not focusing on small fields as we have seen before, but we also can go on a larger scale, like the full filter surface, as shown here, showing several larger particles present, but also smaller ones and potential fibers. On a data level, we're not only getting the polymer types and sizes, as an example shown here, as we found on this example, a lot of rubber type 3, polypropylene, and polysulfone. And polysulfone was one of the materials we have overlooked using manual analysis. We also can combine it with the size classes, so we get even more information and far more detailed information, not only on the particle sizes present, but also their chemical composition in relation with their size. And especially if we look for larger size particles, they often have quite a difference in contribution of the polymer type compared to smaller ones, especially if you look above 100 micron in this example. So this indicates that we need to go best as possible for every particle size using spectroscopy. And you've seen the example before. This is the area analyzed with the MCT detector, now analyzed using chemical imaging with a 2.7 micron pixel resolution, and afterwards followed by automated analysis. And here we were using Simple again, and Simple uses this data to first produce a heat map to show that the information is valid. See here, for example, these residues of the diatoms, as well as here. And you see that we gain quite a similar information in detail about this particle. After automated analysis on the same area as analyzed for particles, we found 10 plastic particles made of 4 different polymer types and also identified 16 non-synthetic particles. In our case, we added non-synthetic particles to the database to avoid misidentifications. A typical example here is polyamides, as synthetic polyamides and natural ones like keratin or the typical skin surface look extremely similar. And finally, with this method, we achieved harmonization, as we have a data analysis independent from human bias. You do the automated analysis, and we can identify and quantify microplastics within the one process. So we do not need to separate these processes. We can save a lot of time by performing this analysis in parallel. In our first studies using Opus, we were needed to do this because the process was rather slow compared to Simple. But still, we can have a high comparability of these results, either analyzed via Opus or via Simple. And we used it now in a lot of studies. You see here our current literature using this method for water samples, treated wastewater samples, sediments, sea ice, snow, and biota is currently in progress. And as mentioned earlier several times, we also transformed this process into a software device called Simple. In the following, I will concentrate on a few selected examples on treated wastewater and give a short introduction about the performance of SIMPLE. With a look on treated wastewater, we performed a follow-up study together with the colleagues of the University of Bayreuth, of Professor Laforge, and again with the OWWV, the Water Board of Oldenburg and Istria, and two selected wastewater treatment plants. On the one hand, Oldorf, which had the highest emission rate, and Oldenburg, which has a post-filtration unit, sampling at 2 days. The samples were treated in the same manner as in the original study, but now analyzed with the automated process. And you see we had 2 different days and we had 2 different situations. On the one hand, Oldorf, at the 13th of August 2015, had a high emission rate. Still, on the other day, we found even more particles, and especially a lot of particles made of varnish in each of the samples of that day. And in addition, the effluent before the post-filtration unit had then in Oldenburg a higher emission rate than Oldorf compared to the first day, where the emission rates were significantly lower. Still, in both cases, the post-filtration unit removed quite a lot of the microplastics. So we really got in the one example close to values that they are not visible here in the same scale. In the other day, the emission rate were quite higher, so due to a rain event, those wastewater treatment plants were at their limits. If we look for particle sizes, we always see the same type of distribution. We have an increase in particle number with decreasing particle size, typically with a maximum at the lowest size class. Also, if we look now at the post-filtration unit, we see that most of the large size particles are efficiently removed, while particles below 100 micron still pass through the system in significant amounts, at least under the conditions of high rainwater content. In these early studies, we were not able to determine fibers, because fibers, typically very fine, with a diameter of 10 to 20 micron and have a rather high length. Ideally, they would look like this, but in nature, they bend in every 3 dimensions. An example is shown here from a cellulose fiber, where you see here in white a little bit the fiber and more the bending behavior by the shadows from the light, trying to collect this image. Microplastics, or as I said, for microfibers, co-defined in 2016 a minimum diameter to length ratio of 1 to 3 to be defined as a fiber. And how to overcome this issue of the bending is to place a barium chloride window on top of the sample, moving the whole fiber together with all particles of the filter into the focal plane, and then be able to perform the measurement. Still, this comes with some cost, so we may lose particles after measurement when we remove the window, and fibers may overlay. Still, in this study, we were able to measure fibers very well and to apply image analysis. Here we developed a pipeline based on our automated analysis, then using special types of image analysis to determine between particles and fibers. By the application of parameters, we were able to perform a screening on the impact of these parameters and finding the optimal solution. The whole process starts with the labeling of all objects and then determines the sizes and only moves large size particles into the fiber analysis pathway. This is this one. And the smaller ones directly go to the particle analysis. From this large size objects, we do this so-called distance mapping and masking, and afterwards determine the elongation of all potential fibers. Only if we reach a threshold of, in this case, 3 for elongation, we perform further analysis on the fibers, so calculating the skeleton and close the gaps, and then determine length, polymer type, and number. All other materials move back to the particle analysis. In the following, a small example is shown using one of the treated wastewater samples from the same study as before. You see here we find a lot of particles, and we from this method cannot say what is clearly a fiber, what is clearly a particle. By running the process, we get first all fibers here removed and only the particles present, but more interestingly, here we see all fibers. And you see here only the larger sized fibers, because if we look into detail, you see that we have various types of fibers from thickness to size present. This, for example, this one big cellulose fiber here, these smaller ones, polyethylene fibers, but also very fine particle fibers here from polypropylene or polyester, but also acrylates and other materials. So we gain a lot of more information. And this information we can then analyze. You see here the same 6 samples from the treated wastewater plants as before, now separated by their location. So this is the Holdorf example, and these are the Oldenburg examples, day 1, day 2. You see also that in both cases you see these high numbers on the second day. But what you see also is that we move most of the fibers during the filtration, and that we have a dominance of microplastics rather than microfibers. Typically, in literature, microfibers dominate, but if we look down to the small sizes, we see that microplastics still are dominant. And if we look now for the filtration efficiency in these 2 Oldenburg examples, we see that we have a removal rate of 86% of microplastics, but even higher removal rate for synthetic microfibers of 89%, while cellulose microfibers are less significantly removed with 78%. And in total, one could conclude from the study that this post-filtration unit at the effluent removes most of the particles and fibers and prevents them to be released to nature. These 2 examples show you already how important harmonization is. But harmonization is not only limited to the area of data analysis, but the whole process of assessing and monitor the plastic pollution needs to be harmonized. And with this, EuroCharms comes into place. This is a project funded by the European Union's Horizon 2020 program and aims to produce recommendations based on reproducible analytical pipelines determined from existing protocols and methods and tested for suitability and feasibility during interlab comparison to determine the availability within labs, the costs, and the quality of data. This is surrounded by capacity building around Europe to perform these analyses. And finally, to support future static programming for research and innovation into this field. If you're interested, you can simply visit our website and will gain a lot of more information and information on the ongoing process. And now back to data analysis, we currently have some issues. Alone in this field, we have many different data sets available from different systems, from using different databases and different identification approaches like library searches, but also machine learning tools, or even artificial intelligence approaches. What these all need a tool for comparison. So this can be done by either providing the datasets or by independent tools from any manufacturer, which should be available via open access. And in our work, we identified two parts as crucial for success. On the one hand, the database, which should be available for everyone to use, and secondly, a software tool freely available for the analysis of microplastics. And both pathways were already tackled during the Basement project. On the one hand, by publishing a reference database, open access. We will find it here in this publication and apply it. So you see here an example of this particle placed on the air crystal, analyzed. And we typically do 3 measurements, so we're really sure that we identified the particle. Also, within this publication, the same database was further investigated for automated analysis. So most of our results you see nowadays are using this database and this harmonized color code. And to move from our Opus software to allow all people analyzing the samples, we developed the software tool SIMPLE, standing for Systematic Identification of Microplastics in the Environment. It's available under the Creative Commons license on the website www.simple-plastics.eu. And you see here the graphical interface, which allows you to measure chemical maps, where it's designed for, but also single spectra. And with this tool, we were able to analyze data across all systems. So you see here examples from Bruker using the Hyperion 3000 and examples of 3 other manufacturers, which allow the chemical imaging. One instrument is discontinued and the other 2 have a lower resolution. So they use a pixel size of 25 to 20 micron compared to the 10 micron of the Bruker system. Still, in each example we could find microplastics and determine size, shape, and numbers, which means we can compare across all studies the results. And in a summary, we were able by this process to lower the expenditure of time from 24 hours using Bruker Opus to 2 hours, with only having 1 hour of labor time per sample. Other time is then in total linked by the instrument. We have an impartial analysis, and we do a evaluation with a fixed confidential interval via free available software, which we can also compare with other institutes. We have a minimum of personnel requirements, because one person can do this in parallel from several samples and in several instruments, and reduced our measurement times currently to 3 to 4 hours compared to the 16 hours used before using a different lens system. In conclusion, I hope I can show you that microplastic analysis by FDS spectroscopy and microscopy has a low expenditure of time, an impartial analysis, minimum of personal requirements, yields fast and reliable measurements. And with this, I thank you all for your attention, and the whole working group at Xavier and Helgoland, Gunnar Gertz, Antje Wilchels, Jessica Song, our PhD students Lisa Roger, Nick McKay-Roberts, Sirene Abel, Fang Shu Wu, and Clara Leistenschneider, and also former students of the group called Claudia Lorenz and Inge Kirstein, as well as our technical assistants Hannah Jevens, Hilke Döpke, and Markus Bach, as well as all bachelor and master students which conducted the research here. From the AWI Bremerhaven, I thank Melanie Bergmann, Mine Tegmann, and Ilka Peken for all the nice collaborations, and from the Aalborg University, especially Jes Wollertson and Aloise Vianello for all the work together on Simple, as well as PhD students Martha Siemann, Niki van Aals, and Christine Olsen. From the Hochschule Bremerhaven, Fraunhofer Mewis, Professor Richard Rascha Friesenhausen, which developed with us the automated analysis pipeline, Felipe Ambrosio Diaz, who worked together with us on the microfibers analysis, and the funding agencies, especially the German Federal Ministry of Education and Research, BMPF, for funding the project FACTS, and the European Commission for funding of the European Horizon 2020 Coordination and Support Action European Harm. And please contact me either per mail or within the chat today if you have any further questions.
So, I'm back again. And this was it for the first part of our webinar today with Sebastian Primpke. The next part will be done by Martin Seber, who's going to tell you a bit about our solutions. And after that, we have the live Q&A sessions. And I've seen that some questions have already been coming in, and we're going to ask them. And if you have further questions, just type them into the interface to start. So, Martin, are you ready?
Yes, we can start. Hey.
Hi, Martin. Then I just give you the ball.
All right. So we've already heard a little bit about the technique itself, a little bit about the instrument, but I'm going to go a bit into more detail about this before we go to the Q&A session. So you should all be able to see the screen now, and as promised, a bit about the instrumentation. So shortly about me, I'm Martin Seber, working for Bruker since 2017, directly after I finished my PhD. And for some time, I am responsible now for microplastics within Bruker. And the system Sebastian Primpke and the AWI is using is the Hyperion 3000. This is our research imaging microscope, which has a high flexibility in accessories, detectors, objectives, and also an objective with a low magnification, ideal for microplastic analysis. And it's coupled to a benchtop spectrometer that also has its own benefits. The other system I want to talk about today is the Lumos 2 imaging microscope. Now, this is a standalone solution, more aimed for routine work, while the Hyperion is aimed for research work. Of course, both can be used in both scenarios, but the one has more flexibility and the other one is really tailored to a full automation, so an automated approach and an easier handling. And today it also offers the fastest imaging speeds. So a bit more details about the Hyperion 3000. This was one of the first instruments and pioneered and established FPA imaging and microscopy. We have different objectives available. The 3.5x objective is especially useful for microplastic analysis. We have a dedicated 20 times ATR objective for very tricky samples, and a grazing angle of incidence objective lens where you have a 2 pars on the sample to find thin layers on metallic surfaces. We can offer spectral range extension with the base spectrometer, which is configurable from a very basic routine instrument to a full-fledged research instrument with even automated beam splitters. Okay, but coming back to the Lumos 2, this is our fully automated standalone imaging microscope. This is also equipped with a focal plane array detector, so the same technique you have seen in the previous talk. And this uses a 32 by 32 pixel detector, where each pixel is 5 microns in size. So you will really find all the small things. And we have a collection speed of around 750 spectra per second at 8 wave numbers. I'm mentioning 8 wave numbers because this is usually the resolution we're using for microplastic analysis. Okay, so to do a comprehensive analysis, we require a high information density. And this is achieved along with high measurement speeds by the Lumos 2. And, oh, sorry, my presentation just flipped. I will go back into it. So this is really the live speed you're seeing here. Each tile is 1024 spectra we're collecting. And we also have a live visualization, like you see on the left-hand side, which is achieved by simultaneously measuring and evaluating the data we're acquiring. And again, we have quite high speed to make the sample measurement as fast as possible. So we have talked about harmonization and standardization. So what are the expectations in this case? So to make it as accessible for anyone who's using it, the full process should be automated. And with the Lumos 2, we have the full automation of hardware, measurement, and we have seen in the talk, we can also automate the evaluation completely. Another important thing is that it can be used by anyone. So we don't always want to have highly skilled personnel, but anyone who's working in a lab should be able to do that. For this, we offer a guided user interface and a step-by-step workflow of the whole process. And another key aspect when we make sure that everything is working properly, we must make sure that we find all particles on the filter and identify them accordingly. And with the Lumos 2, we're operating at the diffraction limit. So we will find everything that's technically possible. We are measuring complete filters without any further preparation steps. So we don't need aliquots or anything. And we're doing this on the analysis we're doing on full range FTIR spectra. So we have the full information from the filter. Everything is covered by FPA imaging, and we can use the full range for the identification, which also leads me to the next point. This system can measure any kind of sample. And we have, on the one hand, FPA imaging that tolerates large amount of foreign particles, a large amount of debris. I will show an example on the next slide. And thanks to the spectral range we have available, we can identify all kinds of polymers. So nitriles will be covered, and also the full access to the CH and CN region, NH, makes it very easy to really identify everything. And what we also need is reliable and reproducible results. And for this, the Lumos 2 has a self-diagnosis we call PermaSure to make sure that the instrument is always working within specifications. And we have high quality FPA spectra we will use for the identification. So just a very quick example before I finish my talk. Here we have a filter that's very heavily loaded. You see there's a lot of sand on there. We have a lot of plant materials and also some coal pieces. And we're measuring this whole filter in the process. And all this, what we've seen, does not really impact the measurement negatively. So we measure the whole filter, we create this image with all the chemical information available, And thanks to automated evaluation, it's easy to create a report that shows the distribution on the filter, the identity on the size filter, the size of the particles, and also the total amount. So it's really easy to just create a report. That was already everything I wanted to tell you from my side. So thank you very much for your attention. And I head back to Simon, who will open the Q&A session.
So thank you very much, Martin, for your part here. And some questions have been coming in, and I hope that Sebastian Primpke is also ready to take some and answer a few of them.
Yes, for sure.
Okay, thanks for joining us again. It's very nice to have a real expert on microplastic analysis to talk to today. Let me share my screen for that we have something to look at besides our faces. Okay, so first question, you talked a lot about harmonization and FTIR analysis, but there are other techniques as well. Could you say something about the harmonization efforts there and how it compares to FTIR?
So what we as other techniques have available is, as I mentioned in the webinar, is for example pyrolysis GCMS and also Raman spectroscopy or microscopy. Yeah, those are currently under investigation. How they differ or what information we can get. Is it similar? For example, we conducted a study using anodisk filters, which we first analyzed using FTIR, and which was followed up by pyrolysis GCMS by simply crushing the filter. And here we could find that we find, for example, the same trends in polymer composition, but not in polymer numbers, but differences in polymer composition due to the different approaches how a particle is identified. As we in FTIR go for numbers, we also get the smaller size particles. But if you have a large particle in pyrolysis GCMS, it contributes a larger mass compared to a small particle. And these fine details are now coming into the field of research to say, okay, which method is optimal for your question. If you go for really fine particles, for example, below 10 microns, so the diffraction limit, it's often seen that Raman microscopy made the optimal technique. But if you there go for a large number of measurements, the time gets an important factor. So a Raman measurement takes approximately a day, depending on your system and level of details you will get. While, for example, our FTIR measurements in our current settings take 4 hours, and the Lumos will be even faster. And so this is what we need to take into account for harmonization.
Okay, thanks. That you talk about time is a good place, because I have a question here that is asking, how long does it take to analyze the average sample? In this case, the average sample was mentioned with a 2x2 centimeter filter with sediment microplastics. But is this the case, 2x2 or?
What we normally use is 1.5 times 5.5 millimeters as field of view, which we measure. But we are using for example, a larger anodisk. So we are working with 25 millimeters anodisk filters, which have a polypropylene support ring, just to make it easier to handle. And these, we choose a smaller concentrated area compared to the full filter size. This has two advantages. On the one hand, we have not too much of this PP ring in our spectra, and the small amount we can then use as standard if the measurement had gone well. But on the other hand, if we reduce this area, we can avoid this typically so-called coffee ring issue on filters, because we apply a smaller area for the vacuum than our filtration funnel has, and this gives us an even filter distribution. So avoiding these dense overlay of particles, which is an extra problem for FTIR and all other techniques.
Okay.
From analysis point of view, as I mentioned, we take around 4 hours to measure such a large size. with 32 scans, which we commonly use per field, which we measure.
Okay, thank you very much. Martin, you have anything to add, or can I go to the next question?
Yeah, just as Dr. Primpke mentioned, the Lumos will increase the speed a little bit. So when we're talking about 4 hours, in his case, we will need 1.5 roughly to cover the same area.
Okay. Then let's continue. Another question about the filter, at least I interpret it that way. What is the biggest area of a filter sample that can be analyzed at once?
At once, using the Opus 8.5, I think there's no limitation. It's a time limitation, more or less. But currently I measured with the system using even the 36 times lens, we have a really large field compared to what we were able to use in previous version of Opus. And I haven't seen yet any limitation in field size. It really depends on the time you have and the objectives available.
Okay, Martin, is there any hardware limitation to the sample size?
No, we do have a stage limit of the sample size, but usually that is not reached. No, and we also do not have a measurement size limit. So everything you can fit in your hardware, in your RAM and on your hard disk, basically you can measure it. Just keep in mind that the analysis time will increase and the measurement time the larger the filter is. So in general, it's more beneficial to use smaller filters.
Okay, but the sample stage limit would be like 8 centimeters, right? Roughly.
We are at 7.5 by 5 centimeters.
Okay, thank you. Let's continue. I'm just putting the question out between you both. I'm doing microplastic in surface water analysis. What is the suitable sampling method?
So for waters, it's really depend where you look on, because we have various size ranges available, and what typically is done often is using a manta net or a Neusser net, which has an aperture of 100 or 300 micron. This is typically used for larger particles, but large water volumes. If you aim to go for the smaller size particles, the use of pump filtration systems is I would suggest to use. They have a smaller sample volume, but they can cover, you can give the minimum particle size you measure with the filter mesh you perform the filtration on. And this is, during the current literature review, also one of the most applied methods to going for these small sized particles.
Okay. Very specific question. Thank you very much for this interesting presentation. I just wanted to ask if something like a list of institutes, universities that own a Lumos 2 is accessible. Martin, do we have a list of reference customers or something like that?
Yeah, we do, but we are limited in what we may give out because of data privacy protection.
Yeah, but when I remember correctly, we have made a collaboration with the University of Bayreuth, and Sebastian Primpke is also here today. So at least
Yeah,
there are. So we have at least two. Well, Sebastian Primpke, you are not using the Lumos at the moment, but I think in Bayreuth we have one, right?
Yeah, this we can freely disclose and mention, and Martin Löder, who is using it, is also happy to present the system. So this is definitely something we can show.
Okay, let me check the other questions. Yeah, so I think this goes into the direction of the daily user. So when using the anodisk filter, the anodisk is very thin and brittle, so it breaks sometimes during sample preparation and analysis transfer. Is there any handling experience that you could share to make this person's life easier?
So first of all, we are using the PP supported ones. So we know that we have a PP ring attached to it, so a potential contamination source, but in our blank values, we don't see it any part of the filter. So we clean them prior to use rigorously by applying pressured air. And you see already, if they have the support ring, they are not as brittle as the unsupported ones. So we can, the 25mm we have rarely any breakage, or because they are really well to handle if they are supported. And a few of these filters we analyzed now 10 to 8 times for as using as a reference for method development. So they are quite stable. What is important is here we need to clean them and to use the field of view in according to the size of this PP ring. It may impact the automated analysis approaches available. Still,
Okay, so
it's a good internal standard.
Okay, so the secret to having this brittle filter material is the PP ring, and if you get those, you should be fine if you clean them.
Yes.
That sounds great. Let me get to the next question. Oh, maybe that goes to Martin, but let's discuss. This user asks if he understood correctly that our instruments can determine particle size and identity of sediments without the need for cleanup procedures. Is that true, or was there something misheard?
Partially. So I would not agree that it does not need any cleanup. This will not work. And what you've seen here is basically the worst case that can still be measured. So it does not need to be perfectly clean. There can be still some sand on it, but if there's too much, it will still cover the particles, and then you will not find them. But it doesn't need to be perfect. So if there's still something left, it's okay.
So the method itself is quite robust, but there are ends to it.
Yeah, this is a good way to put it.
Yeah, Herr Primpke, anything to add here?
There's currently no method available which can analyze a full, really environmental sediment sample, for example, from marine environment for microplastics without any sample preparation. It may be different, for example, using TED-GCMS for highly contaminated samples, but this isn't also would be possible for FDA because they have such a high load of particles. But in the regular assessed microplastic samples, one at least needs a density separation, or in addition, a chemical treatment to analyze for microplastics, independent which part of the reaction they prefer.
Okay, that was the last question. So thank you very much, Sebastian Primpke and Martin Seber, for joining me today for this webinar. It was great. One last question, okay? But then we finish. That's the last one. Martin, I think that goes to you. Have we any experience on using the Lumos 2 FPA imaging system for silicon filters?
Yes, we do. So
can you tell us something about that?
Sure. So it basically works the same way as when you're using an aluminum oxide filter. You can put them in a holder and measure them fully automated in transmission. The only thing is that you might increase the measurement time a little bit because these tend to scatter a lot of light, and so the light throughput is not as good. So you might increase your measurement time a little bit, but the end result will be perfectly fine and usable for any kind of sample as well.
In particular, this person is asking about a silicon filter with 500 microns thickness.
It's not only the thickness, it also depends on the coating. So it's hard to tell, but 500 microns sounds like it's no problem.
So maybe there's something else wrong with the filter here.
No, I don't know what the spectra actually look like. So we recently got some filters we are also offering. Those are 300 micrometers thick and have an anti-reflective coating. And with these, we get very good results, well, for transmission measurements with FPA imaging.
Sebastian, what's your take on the silicon filters?
As we stick to the nanodisk, we try to evaluate some silicon filters, but it occurred that they have some other issues which we simply did not further investigate because we are our routine filter with AnnoDisk.
Okay, so and I think in that you both say AnnoDisk is the best way to go at this point.
Yes.
Okay. So I hope this answers all the questions. Thank you both for your time, and I hope to see you again in another webinar maybe. Thank you all for listening in. And with that, I will close the session. Goodbye.
Goodbye. Thank you very much.
Bye. Thank you.